In this segment, we'll look more at dynamic allocation and at how to recycle runtime heap space to avoid dead storage. The second big advantage of dynamic allocation, aside from being able to create variables on demand, is being able to avoid dead storage and instead reuse the same memory for different variables as the program runs. It's not uncommon to need a variable for a while but then be able to dispense with it. We could do that by just losing track of the variable, changing our pointer to point to a new one, as we did in the line 15 through 18 loop here. But to avoid dead storage, we really want to mark the unwanted variable's space as available for reuse so that it may satisfy the memory needs of later malloc calls. We do this by calling the library function free, which is the partner to malloc. You pass to free a pointer to the dynamically allocated variable you no longer need, and free marks its space as reusable. And then future malloc calls will use the space if it fits their needs. The loop on lines 21 through 25 is nearly the same as that on lines 15 through 18, except that it's allocating ints instead, and it includes a free call. As you can see, we keep each allocated integer from the malloc only long enough to print its address, and then we free it back into the available space of the runtime heap. As you can see from the output, the space is indeed being recycled because each malloc call returns the same address, reusing the same space for each ostensibly new integer. Pictorially, what's going on here is that we are recreating a new integer with each malloc call, and then marking it as free, so reusable, and then creating it again, and then marking it as free, reusable, and the same space is being reused over and over again. This ability to recycle memory is one of the biggest advantages of dynamic allocation. Like any good recycling program, the dynamic allocation system takes a limited resource, memory, and makes it last longer by reusing it. Now, a common misunderstanding I want to head off here regarding free is that a statement like free pi frees pi itself. The pointer is just a local variable. Its storage is not on the runtime heap. It's pi's target, in this case an integer on the runtime heap, that is freed. Be sure to have this clear. It's yet another case where we have to distinguish between a pointer and its target. And the way the line reads, it's so easy to think, oh, it's freeing pi. But it's not. That frees pi's target. Now, we might reasonably ask whether careful memory recycling is all that important, given that the runtime heap is several gigabytes large on a modern computer. A small program that's sloppy about freeing storage and runs only for a short time may get away with it. But any professional code is expected to carefully free all storage obtained via malloc once it's no longer needed, and never to create dead storage. Especially if a program runs for a long time, even one missing call of free, if repeated over and over again in a loop, will progressively build up more dead storage until finally the runtime heap is choked to the point where malloc calls will fail. This kind of bug is called a storage leak, as though memory were sort of gradually hissing out of your program like air from a slowly leaking tire. It's an especially insidious bug because it often won't show up until the program is run for a long time. You don't want to find out about your missing free call when the deep space probe is past Mars or when the nuclear power plant control system has been running for a year. Lines 28 through 31, just for fun here, illustrate what happens when you omit a free call. The loop makes several very large allocations, so we don't have to wait a year for the storage leak to build up. To make a quick edit there, sorry. You don't have to limit your malloc call to just a few bytes, by the way. You can ask for as many as you like, even 800 million, as I'm doing right here on line 29. In fact, we'll use such large allocations in the next module to create dynamically allocated arrays. Now, given that we're not freeing any of these big allocated blocks, you can see from the output that after a few calls, as we do this print on line 30 each time, we wind up with a return value of 0 from malloc. Now, that's not an address in the runtime heap. It's malloc's way of saying it cannot reserve what you requested because it has run out of space. This is what happens ultimately when you have a storage leak. Your mallocs start to return 0. And that 0 pointer value, by the way, deserves some discussion. We often need a way of indicating that a pointer doesn't point to anything. The return value of malloc when there's no storage left is just one example. In another lecture or so, we'll be looking at linked lists in C, which also need occasionally a pointer to nothing. In C, such null pointers are represented with a 0 address value. There's never a good reason to actually point to address 0, so using 0 to mean points nowhere works well. The standard C library even includes a #define of nulls so that you may making it equal to 0, so that you may compare or set pointers to 0 using the #define null instead of an explicit 0. Always use null, as we do on line 31 here, to end the loop when malloc returns a null pointer.